Hello everyone, my name is Gong. I'm a research scientist at Apple. Today I'm going to talk about Acustico, surface tap detection and localization using wrist-based acoustic TDOA sensing. This work was done during my internship at the Facebook Reality Labs, where I was advised by Aakar and Benko. Before I talk about motivation and related work, first of all, I just want to quickly show you what is Acustico and how it works. Acustico is a passive acoustic sensing approach that enables tap detection and 2D tap localization on uninstrumented surfaces using a wristworn device with 2 accelerometers and 2 microphones underneath. For example, in this AR calculator app, user can input the numbers on any surfaces nearby and get the calculation results. I will talk more details about implementations and applications later in this talk, but before that, let's start with motivation and related work. As computing devices become increasingly ubiquitous, there is a pressing need for the input technologies that can be always available. While wearable devices like smartwatches enable always available touch input, it comes at the cost of small physical size, which limits users' input due to the fat finger problem. To mitigate this problem, in UIST 2016, we proposed a wristwell that leverages the wrist as a joystick to perform a 2-dimensional continuous gesture input without using the touch screen. 1 year later, we presented Pyro by taking advantage of the area around the device to provide an expanded volume for subtle gesture input. This time, we looked into another potential solution, exploiting the surfaces in the environment around us which provide a large area for accurate and comfortable input. We developed a sensing technique that can detect and localize taps on instrumented surfaces using a wristworn device. So before I dive in, first of all, let me briefly explain how our Acustico works. Where the finger taps the table, vibration can propagate outwards from the point of contact through the air, which we call sound wave. This is in contrast to the vibration propagates through the surface itself, which we call surface wave. We used 4 sensing elements on the bottom of the wrist to detect whether the leading edges of the surface wave and sound wave reach them separately. 2 microphones on the front sense the sound wave, while the 2 accelerometers on the back sense the surface wave. Based on the time differences of arrival between each pair of the sensors, we localize the tap in 2 dimensions precisely. We are not the first one trying to use time differences of arrival analysis to interpret the tap location. For example, Tofi augments the mobile devices and laptops with 4 piezo sensors, similar to the accelerometers we used, and demonstrates accurate angle interpretation for the touch events around devices, just like this video shows. However, we are the first to embed acoustic sensors in a wristband form factor to detect and localize finger taps. The wristband location form factor introduced 2 primary challenges. First is the small distances between each pair of the sensors. Due to the small form factor of the wristband, the distances between each pair of sensors are much smaller compared with existing work. For a regular wristband, it is usually like 4 cm times 1.5 cm. So this requires a more precise estimate of time difference of arrival. To mitigate this issue, we first included both accelerometers and microphones in our wristband and calculated the time differences of arrival between these 2 different types of acoustic sensors. Since the propagation speeds in the surface and air are different, this would actually add extra time difference. Let me show you a simple example to explain why. Let's assume there are 2 taps C and D that are aligned with 2 sensors A and B on a wooden surface. We assume the signals that are captured by sensor A and B have propagation speeds of VA and VB respectively. With that, time difference of arrival between sensor A and sensor B when tapping at C should be BC over VB minus AC over VA. Similarly, time difference of arrival between sensor A and sensor B when tapping at D should be BD over VB minus AD over VA. Our goal is to maximize the difference between these two time differences of arrival so that these two taps can be easily distinguished. If sensor A and B are the same, this means that VA equals to VB equals to a constant V. Adding this constraint, we can easily know that there won't be any differences between these two time differences of arrival. However, if the sensor A and sensor B are not the same, let's say sensor A is an accelerometer and sensor B is a microphone, then we have propagation through a wooden surface is about 2 times faster than the propagation through the air. Populating this relation into the formula, we can get the difference between two TDOAs is not 0 anymore, it's CD over VA. We actually add actual time difference by using two types of acoustic sensors. And then, we also selected highly sensitive accelerometers and microphones in our wristband prototype and leverage a DAC that can support as high as 1 MHz sampling rate. We use this custom hardware setup to capture the small time differences of arrival. Here's our wristband prototype. After testing many different types of acoustic sensors that are available on the market, we choose 2 accelerometers and 2 MIMOS microphone breakouts that are most sensitive to the tap signals. 4 sensors are situated on the bottom of the wrist with a mechanical structure. Accelerometers were connected to an ICP signal conditioner, which is used to amplify and filter the raw signal. Because we are targeting at the time differences of arrival in microsecond level, we use a picoscope DAC for sampling the signals from both accelerometers and microphones in 1 MHz. And further, the second challenge of a wristband form factor is the inconsistent coupling between the sensors and the surface. Since the accelerometers are embedded on the bottom of the wristband, the coupling between the accelerometers and the surface highly depends on how users put their hands on the surface. And the accelerometer signals may also be affected by any hand movements right before the typing. Both introduce noises and instability in the received signals at accelerometers. This inconsistency makes it difficult to reliably locate the taps by simply using mathematical triangulation. To allow for more tolerance, we choose to use a machine learning regression model to estimate the tap's 2D coordinates. So to be specific, first of all, the raw sensing data from 2 accelerometers and 2 microphones are collected and sliced using a 0.1 second sliding window. And then, within the sliding window, we use 4 different methods to estimate the time differences of arrival between each pair of the sensors. For example, we calculated the time differences between the first peaks, or minimum peaks, or maximum peaks. In total, we have 24 features. After the feature vector is packed, we fit it into 2 independent random forest regression models, one for X position and the other for Y position. We use the output from the models as our 2D tap coordinates. Before I talk about the evaluation, let me first show you a short demo video. As you can see here, the system can detect taps using a simple threading algorithm based on the sensor readings, and 2 independent regression models for both axes are used to interpret the tap location in 2D. To validate the accuracy and robustness of our sensing system, we ran a 20-participant user study. Since the surface made of different materials have different properties and wave propagation velocities, to fully evaluate the system's performance, we asked participants to tap on 4 stools made of wood, plastic, glass, and steel. We also included a sofa arm to see how the system performs on the non-rigid surface. For each surface, participants were asked to wear the device on their non-dominant hand and tap at a 3x6 grid using their finger pad. Each target square is 1 cm by 1 cm, so we have 18 taps for each section, and we repeat this for 4 times. For wood surface, we tested more conditions. We asked participants to tap using their fingernail instead of finger pad. We are trying to see if using fingernail to tap will improve the system's performance because the sound is clearer. And we also included a 2-hand configuration where participants were asked to use their dominant hand to tap, just like this figure shows. The reason why we want to include this condition is that we try to see how system performs without the influence of hand movement on the accelerometers. We calculate the leave one section out accuracy for each participant under different conditions by training the model using the data from 3 sections and testing it using the remaining section. Due to the time limit, I won't go into the details of the results. Here are several primary takeaways. First of all, average error distance across all conditions was 7.5 mm for x-axis and 4.6 mm for y-axis, respectively. Second, steel surface had the best performance, while sofa arm had the worst performance. It might be because the steel surface is homogeneous, which reduces the dispersion and reflection of the surface wave, while the sofa arm is just on the opposite side. Using fingernail to tap did not improve the performance. And lastly, two-hand condition is better than one-hand condition, since the effect of hand coarse movement on the accelerometers was completely removed in two-hand condition. We also looked into feature importance of TDOA features from each pair of the sensors. As you can see in this figure, for y-axis localization, the TDOAs from different types of sensors proved more important, which validates our idea of using propagation speed difference in the surface and air to add extra time difference and improve the sensing resolution. That's for the study results. Next, I'm going to show you the demo applications. We built 4 demo applications to showcase the possibilities of Acustico. The first application we built is a dial pad for AR devices. User can simply tap at different locations to enter a phone number and call the person he or she wants to contact. Similarly, we also developed a calculator for AR devices as I showed at the beginning. User can input the numbers on any surfaces nearby and get the calculation results. Our third application is a Wreck-More AR game. Users can hit the mouse by tapping on the surface, which offers an immersive gaming experience with corresponding haptic tactile feedback. Finally, we combined Acoustico with an optical throw sensor underneath to additionally track the user's forearm motion on the surface. Using the optical throw sensor, we created a mouse experience where users simply moves their wrist to control the pointer position. Left and right mouse click are invoked by user tapping either on the left or right spatial location with respect to the wristband. We believe this can be a good alternative input approach for a remote display. With that, I would like to conclude our work with 3 take-home messages. We present a passive acoustic sensing approach for wrist-worn devices to detect and localize taps. Our system can reliably detect taps and yield high localization accuracies across different surfaces. We believe Acoustico holds the potential to further enrich the input expressiveness of computing devices. That's all I want to share about for Acoustico. Thanks for listening.